This next identity is called the multiplicative identity. It tells us that if we have here that a certain n combination R, or ways of taking R elements in the set of n elements, can be expressed as a ratio of n and R times the combination of n minus 1 and R minus 1. We are going to prove this here. Again, this is known as multiplicative, because we have here a factor of the ratio of n and R to be multiplied to whatever be the combination here. Now, before we will start with our proof, it's important for us to remind ourselves that if we have here n combination R, this is actually n CR, or again n combination of R, in formula is equal to n factorial over R factorial times n minus R factorial. So we are going to manipulate the right hand side here, okay, in such a way that we could yield this result, which is just equal to the left hand side. We're picking here to manipulate the left hand side because it is more complicated, as it would lead to the left hand side, which is the simplest form. By the way, one thing that I have forgot to place here is the restriction that our R is greater than or equal to 1. Why is that so? Because as you can see, we have here R minus 1 elements. If this is actually equal to 1, so we are also going to have 1 minus 1 0 objects. So we are rearranging 0 objects, or we are taking 0 objects. That's still in the realm of combination. But if this is otherwise, let's say if we have 0, so 0 minus 1, we have negative 1 to be taken from the set. So it's no longer possible. Hence, we have here the restriction of R greater than 1. Let's have here our proof. So again, we will be manipulating the left-hand side. That's n over R times the combination n minus 1, R minus 1. So with this now, let's try to expand this combination form using this formula here. This one here. Take note that our n minus 1 is the number of elements in the set, and R minus 1 is the number of elements we're taking from the n minus 1. So with that, this means that our n minus 1 corresponds, for our n here, which stands for our numerator and the factor, or one of the minuend of our minuend of one of the factors in your denominator, and your R minus 1 is actually this one here, which corresponds to that. So you're looking into the correct form, so you will have here times again, so we have here n minus 1 factorial, that's for your, again, what happened here, over your R originally, but here R minus 1, so you have here R minus 1 factorial, and then you will have n minus R, which is actually the difference of these two. Okay, so you will have here n minus 1 minus R minus 1, and whatever be the result, factorial. Now, our goal is to show that from this we will yield to this result, which gives us this form, the original left hand side. So by manipulating that, let me use other color here, or later probably. So you'll have here n over R times n minus 1 factorial, hopefully you're following, over your denominator will still be R minus 1 factorial, and this, by removing the grouping symbol preceded by a negative sign, you will have here n minus 1, or you can remove the grouping symbols now, so you have here n minus 1 minus R, but the second term would be plus 1 because of a double negative property. Moving down, this again, n over R times still n minus 1 factorial for our numerator. One of the factors of your denominator is still R minus 1 factorial. What happens here is you have minus 1 plus 1, which is 0, which returns to only n minus R factorial. Again, this is because you have here minus 1 plus 1, that becomes 0, so that is why it's n minus R factorial. Now, since both of these terms are now in fractions, so it's easier for us, this one in here. Of course, when you multiply fractions, numerator to numerator, that's n times n minus 1 factorial over your denominator R times R minus 1 factorial, then you have your n minus r factorial. Now, I would like you to focus on our numerator here. What is this equivalent to? This is just actually equivalent to n factorial, or let me write it here, n factorial. Because if you're going to expand n factorial, we know that to be equal to n times n minus 1 times n minus 2 until 2 times 1. But this portion, okay, that portion is just equal to n minus 1 factorial. Okay, so again, this is minus 2 here. So what happens then is your n factorial is just simply n times n minus 1 factorial, which is this numerator. That is why the product of these two is just equal to n factorial rather. All over, same concept will follow to this two, given to this and that relationship there, only represented by r factorial, and you have your n minus r factorial on your denominator. Now, let's stop here and go back to the original form. Look into this form here. Okay? This form here. That's n factorial all over the product of r factorial and n minus r factorial, which is equal to n combination r. Now, that's actually the result here. So this is actually the expansion or the result when we multiply n over r and the combination n minus 1 and r minus 1, which is equal to, again, n factorial over r factorial times n minus r factorial, which is just equal to n combination r. So we can have here the final statement because we are proving. Hence, you will have here n over r times the combination n minus 1 and r minus 1 is just equal to n combination r, or if you would like to rearrange it, n combination r is equal to the product of n over r and n minus 1 combination r minus 1. This is the proof for this identity. I will not be giving here specific examples because you can actually look into that when you try it on your own. Okay, so you can try this on your own. Say for example, if n is actually 5 and r is equal to 2, so for this portion you will have here 5 combination 2, and for the left hand side you have 5 halves times 5 minus 1 combination 2 minus 1, or just equal to 5 halves times 4 combination 1. Check by using your calculators if this is equal to this expression as represented by this identity. I'm just gonna leave that to you. After all, the purpose of this video is only for proving this given property. Thank you very much for watching.